The last thing what I introduced was equivalence. I told you equivalence is a concept of dividing the molar mass into certain number of equal masses which will be combining either with hydrogen, oxygen or chlorine. How much of oxygen? 8 grams of oxygen, 1 gram of hydrogen or 35.5 grams of chlorine. Now that mass of a particular compound which reacts with this oxygen, hydrogen or chlorine is called as the equivalent mass of that compound. Okay. So you can see in a chemical reaction, got it? Equal number of equivalents of reactants, with each other to give equal number of equivalents of products. In simple term, suppose if I take a reaction like AA plus BB, CC and DD, the number of equivalents represents how much weight by equivalent weight a molecule, element or a species would have. That is called number of equivalents. So suppose if I check the equivalence of A, maybe let's say I calculated the equivalence of A by some method, then the equivalence of B, C and D, right? The amount which got reacted and the amount that got formed in terms of equivalence will always be same. And this is called as law of equivalence. Got it? For example, the number of moles here could be different, but the equivalents which have been reacted and try to form product will be same. Got it? So in case if you have any compound AXBY like Me3N2 or ammonium sulfate, any of this form, the number of equivalents of AXBY taken is always equal to number of equivalents of A and number of equivalents of B, sum of these two. Got it? For example, if I write what is one equivalent of AX and BY, okay, so then the equivalent weight will be, or the equivalent weight of AX BY will be equal to equivalent weight of A plus equivalent weight of B. See, here it may be X and Y of any values. They does not play any role in identifying the equivalent weight. It's not like there is something multiplied or divided there. It will be equivalent weight of A plus equivalent weight of B simply. Okay. Or in short, equivalent weight of a substance is equal to molar mass of a substance by its N factor. Got it? N factor can never be 0. It could be either 1, it could be greater than 1, or it could be less than 1. But it can be never 0. Clear? Yes, it will be positive value. Less than 1 means it will be greater than 0 and less than 1. It cannot be negative value either. Okay. In fact, we take it as a magnitude only. So the magnitude of a value will be its N factor. Got it? The other day I told you, in case if at all I take 1 mole of a substance, let's say this is 1 mole of a substance, weight of something of 1 mole. Then the number of equivalents present in that will be equal to 1 mole into its N factor. Okay. So N factor is the number of divisions that you are making for this weight, considering it like a box. So imagine a box of weight, or it's like, loaf of bread and freshly prepared bread. And now you're cutting them into slices. Then the number of slices you make, correct? On how many total number of slices you get, that will become the valency factor. So one equivalent is the mass of that box present in and that is called as equivalent mass. Okay. So N factor is the number of equivalents present in that 1 mole of a substance. Clear? By definition, I hope all of you got some idea about what is equivalence by now. Okay, equivalence you have to learn in two ways. One is equivalence will always be equal to number of moles into valency factor. This is first thing you need to remember as a definition. Okay, equivalence can also be written as weight of substance by equivalent weight of a substance. Equivalent weight again can be related as molecular weight upon valency factor of a substance. Got it? So this is the interlink that you need to connect. Correct? To see the main variable here to figure out equivalence is equivalent weight, and equivalent weight is mainly dependent on valency factor. Now let us see what exactly it is. There are different types of reactions, but broadly we classify them into two kinds. One is a redox reaction, the other one is a non-redox reaction. Okay. Now reactions in which the oxidation number of the element in a compound changes. If the oxidation number in a compound changes, then we say it is undergoing a redox reaction. And there are two definitions we'll be using it here, which I iterated earlier: reduction and oxidation. Reduction means decrease in the oxidation number, oxidation as in increase in the oxidation number. Oxidation value, if it is increasing, going towards the positive value, that means it is getting oxidized. It is under oxidation. If it is going towards the negative value or a smaller value, that means it is undergoing reduction. Now, both oxidation and reduction happens simultaneously. You cannot have a half reaction. If there is an oxidation, simultaneously there has to have a reduction. And you see, in redox reaction, electron transfer will take place. Now, coming to the other type of reactions, which are called non-redox reactions. Here, reactions oxidation number does not change. It will remain the same. Best examples, acid-base reactions, where H plus and OH minus is just moving around the ions, but the oxidation state of any of these element or atom is not changing. All the precipitate formation reactions like AgNO3 plus KCl is giving AgCl plus KNO3. There is a precipitate forming. It is like a double displacement reaction. So it is like a double displacement, but there is no redox reaction. That means there is no change in oxidation state occurring. Next, there are reactions where there is some color change, like chromium, which is at +6. This type of chromate is yellow colored solution, while if it converts into dichromate, it becomes an orange color solution. But the oxidation state of chromium remains the same, which is +6. Thus, there is no redox reaction happening here either. Correct? So broadly, you need to understand reactions are redox kind or a non-redox kind. Redox is where reduction and oxidation is observed. Got it? Now notice, number of electrons which has lost will always be equal to number of electrons that we have gained. Okay. So suppose if you have an element M, you are gaining more negative value on it. That means electrons have been added to it and it is getting reduction. If positive values are increasing, as an oxidation state, then the oxidation is occurring more. Okay. So this is a typical detection of electrons being lost or gained. Clear, everybody? This is the major difference between redox and non-redox reactions. Now, our intention is to mostly deal with the redox reactions. Correct? We are not worried about non-redox reactions as of now. Clear? Now see, if you have to, if any chemical reaction is given and you need to figure out whether it is redox or not, you need to check out the oxidation state of typically central atoms which are not a part of general rules. What are general rules? Let me reiterate everybody what we discussed in the last class. The general rules of oxidation state includes starting with fluorine. Fluorine always possesses -1 charge in every compound. Okay, that is the first rule. Second rule is the group 1 elements and group 2 elements will have a fixed oxidation state. For group 1 elements, it is always plus 1. For group 2 elements, it is always plus 2. Group 1 elements include lithium, sodium, potassium, rubidium, cesium. Group 2 elements represents beryllium, magnesium, calcium, strontium, barium. All of them will have plus 2 oxidation state. The third comes hydrogen. Hydrogen could be 0, plus 1, minus 1. If it is connected with metals, hydrogen attains minus 1 oxidation state. If it is connected with non-metals, that means it will always have plus 1 oxidation state. Okay. Then comes oxygen. Oxygen generally has minus 2 oxidation state, but in certain cases it might show peroxy linkages or peroxide formation as well as superoxide formation. Okay, but in general is always minus 2 oxidation state. Now, these whatever has said, right, these are all the important hierarchical uh, statements which you need to remember. Anything other than that, you have to calculate the rest of the elemental values. For example, if you take I2, this is in a pure form. For a pure form, oxidation state here is 0. Okay, I would suggest this you will simultaneously do with me. Okay, so oxidation state of iodine here is 0. Next, Na2S2O3. Now notice it again. Here we can have 2x, which is the sulfur, plus 2 times of plus 1 because nitrogen, sodium is fixed. Oxygen in general is always fixed as minus 2. So that makes it 2x and minus 4 equal to 0. So x is equal to 2 plus 2. So the oxidation state of sulfur is plus 2 here. One sulfur is plus 2 oxidation state. Similarly, I'm again noticing here with the oxidation number only. I'm not worrying about state yet because there are multiple number of atoms. There might be different states also. But let us not worry for that right now. 4x, plus 2 plus 6 times of minus 2 overall equal to 0. So 4x is equal to 10 or x is equal to 2.5. X is equal to 2.5. Correct? So definitely from 2, if it is changing to 2.5, sulfur is changing from 2 to 2.5, isn't it? So from here, oxidation state is changing from 2.0 to 2.5. So zero point 0.5 electron difference is observed and it is getting higher value. So hence it is oxidation. Hence it is undergoing oxidation. While on the other hand, iodine has 0 oxidation state. Oxidation state is 0 and that is converting into iodine here, which is plus 1 oxidation state. So 1 electron transfer is observed here. Okay. So you can see from, sorry, not plus 1, minus 1. This is minus 1 for iodine because sodium is plus 1, so iodine will be minus 1. So you can see from 0 to minus 1, it is actually going more towards negative side. So that means there is a reduction happening. So this is a reaction where reduction and oxidation both are taking place. Got it? Everybody understood this point? Make a note of that it is a redox reaction. So that is a conclusion we need to draw out of it, that yes, this entire thing seems to be fair enough to express this as a redox reaction. Let's see the second one. Again, the known elements you will not bother so much. Only it is the unknown elements, which is not falling under the rules. That is where you will bother to find out the oxidation state. So here I'll be bothering about oxidation state of manganese, which is 7. Then oxidation state of iron, which is 2. Oxidation state of sulfur, which is 6, just in case. I'm keeping sulfur also just in case. Next, K2SO4, H2SO4, I will not be worried about it because here it will remain 6 only. Here also it is remaining 6 only. Here also it is remaining 6 only, which proves that the manganese is actually plus 2 here. And iron here is plus 3 here. So what did we notice? Iron went from 0 to plus 3, which shows that it is undergoing oxidation. While manganese, which is at plus 7, now it is going towards plus 2, which means it is able to reduce it. That means there is a reduction happening in this case. So on one side there is an oxidation, the other side there is a reduction happening. Finished? Right. See the next reaction here. If I take the oxidation reaction for oxidation state for carbon in this case, carbon here will be 2x plus 2 minus 8 equal to 0. So 2x plus 6 and x is equal to plus 3. So the oxidation state of this carbon is plus 3. While manganese, we already learned this as plus 7. And here manganese is plus 2. And CO2 here would be plus 4. These are the respective oxidation states. So from here it is clear that carbon, which is from plus 3, now it has changed to plus 4. So it is undergoing oxidation. And manganese changing from plus 4, plus 7 to plus 2. So it is undergoing reduction. Okay. So yes, this is a redox reaction. But notice it, the same oxalic acid, H2C2O4, it is an oxalic acid. But when you react the same thing with 2 moles of NaOH, a base, okay, then you expect an acid base reaction to happen. That means this will give away H plus, this will take away OH minus and convert themselves into water and Na2C2O4. But in this reaction also, if you notice, carbon has plus 3 oxidation state here. And here, this is also plus 3 oxidation state. Okay. In NaOH also, oxygen is minus 2. Here also it is minus 2. Hydrogen is plus 1. Here also it is plus 1. Got it? So these are the uh, oxidation state. So it is very clear that oxidation state has not changed at all. Thus, this kind of reactions can also exist. In this case, it is an acid-base reaction. Okay, got it. Now, how do we figure out the equivalent weight? If you know the number of electrons transferred, that becomes the valency factor. But if there is no redox reaction happening, then how do we predict? Okay, see, first I'll write the answer, then I'll explain one by one. See, here H2C2O4 plus NaOH is giving an sodium hydrogen oxalate plus H2O. And here, if you notice equivalent weight, when it comes to equivalent weight, the equivalent weight was found to be m by 1. That means m being the molecular weight by 1. Second, H2C2O4 plus 2 moles of NaOH will give Na2C2O4 plus H2O. Now, in this case, it will be molecular weight by 2. Okay. So, this would be the equivalent weight in case of non-redox. If it is redox reaction, you just need to check out how many number of electrons are transferred per mole of a substance in its valency factor. Okay. That is, if you take non-redox reaction and consider the substance is acid, then you will check out how many number of H plus ions it can lose. Okay. Similarly, if the strength of the base here, the substance here, that represents number of OH minus ions, correct? That means if it is a non-redox, then how many number of OH minus a base is able to give, that defines its valency factor. Okay. Similarly, if a substance is a salt, then in case of salt, you will usually check the total charge it is able to give. What is the total amount of charge? Either total positive charge or total negative charge. Now, these three are the factors you would use to calculate the valency factor. Okay, so in non-redox case, you know how to figure out the valency factor here. So, valency factor can be figured out based on these three cases. Okay, but what about n factor in non-redox with a charge on it, like in a case of salt, or simply a ion is given? Then see, n factor for any element is always equal to its valency, and n factor of any non-redox reaction, non-redox ion, is equal to how much charge that is present on it. For example, if you take sulfate, the n factor is 2, carbonate 2, OH minus, which means 1, NH4 plus, which means 1, phosphate, it means 3. So now what will be the equivalent weight? Equivalent weight simply be equal to molar mass, which is 96 divided by 2. Carbonate, which is 60 divided by 2. Here we have carbonate here. So this is 95 divided by 3. So this will be the equivalent weight of various ions, anions. Clear, everybody? Okay. So first make sure that you are clear with the definition of non-redox. For a non-redox, how do we calculate the valency factor if it is acid, base, or salt? And in non-redox, the broad classification of compounds is these three only. Okay. That is how many H plus, how many OH minus, and how much is the total positive charge. And for non-redox also it is clear, I guess, everybody. If you are in a writing, if you are still writing out, the first thing you do it is write the equivalent weights. Okay.
तो इन द लास्ट पेज जो आपने हमें अभी कराया है, सब्सटेंस सॉल्ट, तो ये जो तीन है उनके एक एग्जांपल दे सकते हो, ये तीनों
नीचे
के?
सब वही है बेटा. ओके, नीचे के सारे एग्जांपल्स वही है. ओके.
अच्छा ठीक, गॉट इट सर।
Let's see this. The n factor of a non-redox reactions is equal to how many number of replaceable H plus ions if it is acids. Okay. And how many number of replaceable ions, right? That is how many H plus you can replace or remove out from an acid. That is called the basicity of an acid. That is called basicity of an acid. For example, in this reaction, if you notice, H2SO4 plus 2 NaOH. So basically 1 mole of H2SO4 has lost both the hydrogens. When it is losing both the hydrogens, then the valency factor of H2SO4 is, 2. Clear? So then it will become 2. I guess this part is clear to everyone. Yeah. So now check out what will be the valency factor in all these cases. First, valency factor in H2SO4 will be 2. Valency factor of NaOH. Now remember, valency factor is always to be checked for 1 mole of a substance. So for 2 moles, it is providing 2 OH groups, OH minus. Hence, for 2 of them here, valency factor is 1. Next, Na2SO4. See, here we are checking based on number of replaceable H plus. Here we are checking based on number of replaceable OH minus. Thirdly, now this is salt. This is a salt. In case of salt, you will check out the total positive value or total negative value. That means if you have 2 Na plus and plus SO4 2 minus. So either the valency factor in this case can be written as 2 or minus 2. You can write it as either ways. Clear? But you know that valency factor is always a positive value. So you always have to take the mod of this one. Got it? And what about water? See, water can be thought as both acids and base. If you think as an acid, it has absorbed one H plus from, I mean, being OH minus, it has absorbed one H plus. Hence, we can say valency factor for this is 1. Okay. What have you noticed? Valency factor is 2, 1, 2, 1. So this is 2 and 1. And here also it is 2 and 1.
सर H2O का कैसे क्या एक बार वापस समझा सकते हो?
H2O can be perceived as both acid and a base. Imagine like this. Okay. If it is acid, it will
हम्म.
lose 1 H plus. If it is base, that means it will lose 1 OH minus. Got it?
अच्छा, got it.
Next, H3PO4 and NaOH. Now, how many hydrogens? Actually, H3PO4 can give maximum 3 hydrogens. But in this particular reaction, if you notice, it has not given all the 3 hydrogens. There was only 1 hydrogen given out. Hence, the valency factor pertaining to this reaction only is 1, because it has given only 1 H plus. Okay. So do remember and understand that whenever a chemical reaction is already given, that means its valency factor is already established. Same way, OH minus here, valency factor is 1. NaH2PO4 valency factor is 1. Water valency factor is 1. Okay. So valency factor of all the species in this case is 1. Next one. If you notice the valency factor in the second case here, check it out. H3PO4, it is converting into HPO4. That means there are 2 hydrogens which are replaced by sodium. So there are 2 replaceable hydrogens. And you see there is 1 OH minus here. And here, considering it like a salt, I will have this as, 2 plus, and either it is HPO4 2 minus. So that means either the charge would be plus 2 or minus 2. Got it? And water will be 1. It will not change. Got it? So you could notice that how the chemical reaction itself changes the valency factor. Okay. And see, in example 2 and 3, H3PO4 taken may be same, but the equivalents will be different. Implies equivalents in the reaction is dependent term. Okay. And see, reaction is not mentioned. You will always consider the maximum replaceable values. That means in some scenario, instead of giving a chemical reaction, it is simply mentioned like this, that I took this much amount of H2SO4, you know, and its equivalent mass is X. Correct. So in such cases where reaction is not mentioned, only chemical is mentioned. In that case, you'll always take it as how much maximum H plus and how much maximum OH minus they can give. So check first one. H2SO4 equivalent weight will be equal to molar mass divided by 2. Got it? Maximum. So here it will be molecular weight divided by 3. And here it is molecular weight divided by 2. Why? Structurally, if you compare that, you will have this as HOP, double bond O, DT bond O, and DT bond O. Okay. Sorry. This one. HPO3. Clear? H3. 1 minute. My mistake. I have this as H here, correct? And when I'm taking about H3PO2, this one is H3PO2. And if I'm talking about H3PO3, then I will have this as H here and OH here. Now, the replaceable hydrogen is this one in this case. And here there are 2 replaceable hydrogens. Okay. So this one is H3PO4. So it appears in the formula, it appears like it has 3 hydrogens, but it can have only 2 replaceable hydrogens. Similarly, here also it appears like it has 3 hydrogens, but the replaceable hydrogen is only 1. Okay. So this by name you will remember it. Okay. This is hypophosphorus acid. Hypophosphorus acid. And this is simply phosphorus acid. Next, H3PO2 molecular weight by 1, H2C2O4 M by 2 because it has 2 replaceable hydrogens. Citric acid, okay, M by 2. It has 2 OH groups, one above and one below. Okay. Citric acid typically looks like this. We have COOH, COOH, H and OH. This will be the structure of citric acid. So it has two replaceable hydrogens from carboxylic acid. HCl, it has one replaceable hydrogen, MClO4 1, and here also M by 1 in both ways. As a salt also, in fact, it has one more hydrogen which can be relieved also. So both ways it is going to be M by 1. And next, okay, M by, there are two of them lost, so M by 2. Then please make sure everybody is clear with this term. I'll give you a minute's time. Go through everything once. Right, see. If you take n factor of a non-redox basis, we learned that it is about number of OH minus replaceable. Correct? Now notice here, AlOH thrice, when you react with HCl, it has become AlOH twice Cl plus H2O. That means one of the OH has been replaced. Isn't it? One of the OH has been replaced. So here what I could say, AlOH thrice, the valency factor in this case will be 1 because it has given away 1. HCl is giving 1 H plus, so it is 1. And here as a salt, you can notice that overall it will have plus charge and Cl minus charge. Salt will always have ionic form, some X units of plus charge and X units of minus charge. So here that makes it again 1, and water is always 1 in this case. So these are the valency factors. Now suppose the same reaction, if at all I am doing with 2 moles of HCl and 2 OH minus are been replaced. So I will write this as valency factor as 2. Here it is still 1 because HCl is, for 1 mole it is giving 1 H plus only. Here it will be 2 and here it is 1. Similarly, when it comes to here, valency factor is 3 considering all 3 OH minus is lost, and here it is 1 and here it is 3 and here it is 1 again. Alright. So as much as basic reactions are concerned, where OH minus is involved, you just check out how many OH minus were actually replaced. Okay. Now listen, while solving questions, we require a good amount, good shortcut to, go through the questions. So here is the interesting deal. Suppose if I consider a chemical reaction like this, H2SO4 plus 2 moles of NaOH is giving Na2SO4 and H2. It's a balanced reaction. So make sure that there must be a balanced reaction to do this, to use this shortcut. That is the first thing. Okay. So you expect for a balanced reaction first. Once you have a balanced reaction, imagine I know the valency factor of only one species. Other species I do not know. Okay. Here it is easy to understand, but there will be chemical reactions where it becomes difficult to figure out. Only one of them is given acid. The other one is a very big complex here, let's say. And that complex is converting into some complexing salt and with some water maybe or something else like this. So if you have that kind of complexity here and we don't know how to calculate the valency factor of, other three factors except one, which is very well known, like H2SO4 in this case, I know that end of the day it is forming a sulfate. So that means it must be losing both the hydrogens. So N factor here is 2. Now, if I know the N factor of even one species out of these 4, if I know even for one species, what you do to find out its N factor, correct? For N factor of all the compounds here, what you do, you simply take the same value here. So what I got, N factor is 2 you got, right? Take that 2 and divide by the stoichiometric coefficient of that molecule. So it will be 2 by 1 for this one, 2 by 2 because you can see here there is 2. Similarly, here it is 2 by 1 here and 2 by 2 here. Got it? And that makes the valency factor for all of them. Now you can calculate what is the valency for H2SO4. You can know NaOH, Na2SO4 and H2O. Clear everybody? Well, here you can say, sir, NaOH to, हमको पता है, Na2SO4 पता है. Yes, you do know that, but there will be reactions where it becomes difficult to predict. In such cases, you can use this shortcut. Okay. Everybody understood? You just need to know one of them. If you know
Yes,
the hint
sir.
of one of them, divide it by their stoichiometric coefficient, that will become your valency factor. Done, everyone? Right. Check. N factor of a non-redox salt will always be equal to total positive charge per stoichiometric coefficient of a salt. So if you have NaCl, just divide it by 1, molar mass by 1. That means 1 will be its valency factor. AlCl3 plus 3 and minus 3 total charge. So plus 3, or I can take it as minus 3. That will be the valency factor. Okay. Now notice K4FeCl6 plus ZnCl2 giving this plus KCl. This is what I know. Correct? This is how much I know. Now, if at all I need to figure out what is the valency factor in this case. Clear? So what, how do we check this? Check out just like replaceable hydrogens and so on. Here you can see there is a replaceable potassium. There were total 4 potassiums. Now I have only 2 potassiums. Okay. So there itself, you know what is the valency factor. N factor in this case is 2. Got it? Well, if you are not aware, sir, I don't know this logic, how to figure out, then how will I know that? So check out. One thing you know that KCl is a simple salt, and simple salt will have plus 1 here, minus 1 here. So what will be the valency factor here, beta? We know that the valency factor here will be 1. Is that clear? Okay. So if the valency factor here is 1, then how do I predict with all of them here? Correct? I told you that you divide it by that stoichiometric coefficient, isn't it? Okay. So first divide it by the stoichiometric coefficient. So this will become half. This will become 1 by 1. This will become 1 by 1. And this will also become 1 by 1. Okay. Now you cannot have a fractional value like this. So what you do to get a simple integer, multiply everything with 2. Got it? So just multiply everything with 2 here. So what do I get? 2 into 2 into 2 into 2. So what do I get here now? So 2, 2, 2 and 1. These are the final valency factors or N factors. I hope that makes sense, everybody.
Yes, sir.
Right. See the second one now. K4FeCN6 plus 2 ZnCl2 is giving Zn twice FeCN4. Well, using the salt idea also, you can directly figure it out that there are all the 4 potassiums got replaced. So in such case, N factor in this case will be directly, I'm writing directly 4, correct? So if I know that it is 4 by 1 because the stoichiometric coefficients are 1. So this will be 4 by 2, 4 by 1 and 4 by 4. So that makes it 2 here, makes it 4 here, makes it 1 here. So these are the valency factors or N factors. Clear? Copper sulfate is a known salt here. We know that copper sulfate is a known salt. Copper sulfate, copper has plus 2 charge, sulfate has minus 2 charge. So that is clearly giving us the evidence of valency factor should be 2. Correct? So valency factor should be 2. Okay. But notice this. If you are writing valency factor 2 here, again you divide it by 2 here. Correct? So that will become 1 here. Right? And now here you will be writing it as 2 by 1 here, 2 by 1 here, and 2 by 2 here. Isn't it? But it appears like the valency factor is actually 2. So it is misleading, right? In such case, remember that every time you have the if at all you have to apply this logic that you have to divide it by stoichiometric coefficient, you do check out the charge for the total amount of molecules. So for one molecule, copper sulfate, copper has plus 2. For 2 molecules, how much will be the total charge? Plus 4. It should have been plus 4, correct? And that plus 4 divided by 2. Understood? So here again, this will be 4 divided by 1, 4 divided by 1, and 4 divided by 2. So that will be the valency factor. So which is equal to 2 here, 4 here, 4 here, and 2 here. Clear, everybody?
So could you explain
And
the example?
should I explain again?
Yes, sir.
Yeah. See, what I'm saying, let's say if you apply simple logic, let me rewrite that again, okay? Suppose if I take a simple logic here that copper has plus 2 oxidation state. I know this valency factor here. I mean, in that case, divided by 2. So that should fetch the valency factor of all of them, correct? So 2, and this should be 1 by 2. Here it should be 1 by 2. Here it should be 2 by 2, correct? Isn't it? Sorry,
Yes,
sir.
sir.
My mistake. Sorry. 2. 2 by 1. Here it should be 2 by 1 and 2 by 2, correct? Because I have to divide by stoichiometric coefficient.
Yeah.
Stoichiometric coefficient is 1 and 1 here and 2 here. So 2 by 1, 2 by 1 and 2 by 2. So it appears as if the valency factor here is 1, here it is 2, here it is 2 and here it is 2. Here it is 1. But this is incorrect, na beta? This is not the valency factor. We just learned the copper sulfate will have plus 2 charge. That means that is a valency factor, correct? So that creates an unnecessary confusion, okay? That's why what I said is when you have for 2 moles, right? For 2 moles, what is the total charge? Ishman, clear?
Acha.
So for 1 mole of
Okay.
copper sulfate, it has plus 2, na? So 2 moles, how much will be the charge copper will carry? Plus 4, okay? And now you do the division part of it. So this 4 divided by 2. Here also 4 divided by 1, 4 divided by 1, and 4 divided by 2. So that will give you the valency factor. So 2, that becomes the valency factor. Here it is 4, here it is 4, and here it is 2. Done? Check out the same way for FeCl3. See, one one iron ion will have plus 3 charge because each chlorine will have minus 1. So this will have plus 3 charge. So what will I do? 4 3s are 12. So I'll take 12 divided by 4, 12 divided by 3, 12 divided by 1, 12 divided by 1. So check out what are the valency factors in all the cases here. 3, 4, 12, and sorry, this is 12. So 1. Okay. So 3, 4, 12, and 1. These are the valency factors. Okay. This has been asked many times. Correct. This complex has been asked many times in JEE mains exam. This is Prussian blue color. Prussian blue color precipitate. A very important compound for detection of many reactions here. Going ahead, we'll be using this in multiple topics. So do remember what is this formula. Fe4 FeCN6 thrice. Its valency factor usually is always 12. Done, everybody? On the similar lines, check out the last one here. So what is a valency factor? See, valency factor here. Here it is actually having 3 and divided by 1. So 3 divided by 1. Here it should be 3 divided by 1. Here it should be 3 divided by 3. So the valency factor has to be 3, 3, 3, and 1. Okay. So this becomes very easy if you understand how to apply the logic of using the stoichiometric coefficients. Correct? Although these are all, this looks very simple examples, practice is very important. Going ahead, a lot of problems you will come across the issue of identifying the valency factor. So please, gets very hands-on with this kind of examples. Okay. Going ahead now. By chance, if you have a simple compounds like Al2SO4 thrice, you just check out the total charge for 1 mole. So you can see for 1 mole of aluminum sulfate, it is basically divided into 2 moles of Al plus 3 plus SO4 2 minus. So which is clearly showing us the valency factor is 6. Similarly, here also this will convert into 3 moles of barium 2 plus 2 moles of phosphate. Okay. So again the valency factor in this case is also 6. Next one. In case if you have two salts connected with each other, like K2SO4 is also there, Al4, SO4 thrice is also there, and some water molecules are present. These kind of compounds are called as double salts. These are called double salts. So in case
वो
of double salts also,
एग्जाम्पल में वो SO4 वाला 3 नहीं होगा, 3 times SO4 2 minus.
K times,
In that Al2SO4 thrice will be
हाँ
2Al3 plus 3SO4 2 minus, ना?
हाँ बेटा 3, sorry I forgot to write that. Yeah. Hmm, right. So notice this one. Here also if you split it out, so we will get this as 2K plus 2Al plus 3 plus 4 moles of sulfate plus H2O. And H2O does not have any role because it does not take any charge on it. So the valency factor now you will check out is total positive charge or total negative charge. Total positive charge is how much? 2 plus 6, so total 8. So the valency factor for this double salt is actually 8. Clear? Now see, if I want to calculate what is the equivalent weight of aluminum in Al2O3 and carbon in CO2 as per the question. Okay, I mean as per the chemical equation. If I need to find out, what do I do? Check. So two aluminum is in a elemental state. So valency factor is, oxidation state is 0. Oxidation state here is 0. And here the oxidation state is 3. Okay. So for two aluminiums, if we compare, it is 0. For two aluminiums, it is 6. But we need to check valency factor always for one element. I mean one mole. So you can see for 1 mole of aluminum, there will be 3 electron transfer in this case. So 3 electrons got transferred. While oxygen, it is also in elemental form, which is in 0 oxidation state. And from this 0, each oxygen has now -2 charge. So that makes it -6. So how many? So if I talk about here, how many oxygens are there? 3 oxygens are there in total, isn't it? But I need to check out for one oxygen. So for one oxygen, how much will be the change? From each oxygen has -2 charge. So 0 to -2, that means there are 2 electrons transfer. Okay. So from here you can see aluminum here to here, it is giving 3 electron transfer. Here to here, we are getting 2 electron transfer. So you need to check out, if at all I need to calculate what is the equivalent weight of aluminum, you need to check out how many electrons it is involved into. So therefore, equivalent weight of aluminum will be equal to the molecular weight of aluminum, that divided by how many electrons it is involved into, 3 electrons. So the number of electrons involved, that becomes the valency factor. While suppose if I ask you what is the equivalent weight of Al2O3, then what do you do? If I ask you how much will be for Al2O3. Now I know that valency factor of aluminum is how much? 3 for 1 mole. For 2, how many it will be? 6. Correct? So let me rewrite that. 2Al plus 3 by 2 O2 is becoming Al2O3. Okay. So here for one aluminum, 3 electrons are transferred. So for 2 aluminum, 6 electrons will be transferred here. And how do I calculate the n factor? Just now I told you. So this 6 electrons divided by 2. So 6 electrons divided by 3 by 2. And here 6 electrons divided by 1. Okay. So now check out valency factor is how much? 3. Here it will be 4. And here it will be 6. Therefore, equivalent weight of Al2O3, what do you write? molecular weight by 6. So that's how you can write it down. Clear? This is a very standard algorithm. You will never get wrong if you go with the algorithm. Okay? Everybody understood how to go about it? So simply just check out valency factor of any one piece which is known. Usually you will be knowing it very easily from the equation. If you know it for one, for rest of them you can calculate easily. Okay. So molecular weight of Al2O3 by 6. Shall we go ahead, everyone? On the similar lines, check out for oxygen here. For oxygen we have 0 elemental form. Here oxygen has +4 oxidation state. While oxygen O2 elemental form, it is 0. Okay. So here carbon has +4 oxidation state. For two oxygens, that is -2. These are the respective valency factors of each and every element. Now check out from 0 to 4, how many electrons are transferred here? From 0 to 4, 4 electrons have been transferred. And there are two oxygens. Two oxygens still carry 0 charge, and two oxygens will carry -4 charge here. So how many electrons are transferred? 4 electrons transferred. So in both the cases, 4 electrons got transferred. So therefore, equivalent weight of carbon will be equal to molecular weight by 4, which is 12 by 4. Molar mass of carbon is 12. So that is 3. So valency factor of carbon is 3. Next. Sorry, equivalent weight. Equivalent weight of carbon is 3. Next of O2. O2 is a fixed one. You can directly write that as well. Molecular weight divided by O2. But which molecular weight? Molecular weight of O2, not single oxygen. Okay, so molecular weight of O2 is 32. 32 by 4 is how much? 8. And this is what we learned. Equivalent weight of oxygen is always fixed, which is 8. And next, equivalent weight of carbon dioxide. So that is equal to molecular weight of carbon dioxide. Okay. So that divided by valency factor. So how many we can have here now? 4 of them. So therefore, molecular weight of carbon dioxide, how much it is? 44. 44 by 4. Then, so how much it will be? 11. Done. Please do check.
तो like ये उसका n factor of CO2 will be 4. Why? Because 4 electrons are transferred.
Yes.
Okay.
Finished? Concept. Check out the first one. The equivalent weight of metal is double to that of oxygen. How many times its weight of its own oxide is greater than that of weight of metal present in it? Okay. Everybody understood? So first, read the question thoroughly. Check out what he's trying to say. So first, equivalent weight of metal double to that of oxygen, and how many times its equivalent weight of oxide. That means that's why I've written the oxide reaction, because we are discussing about an oxide, metal oxide. So imagine like this, metal plus oxygen is forming some metal oxide, some XY value, we don't know. In that case, how do I write the valency fact, equivalent weight here now? Number of equivalents by definition, number of equivalents is equal to weight divided by equivalent weight, isn't it? So now, if at all I write this as weight of metal divided by equivalent weight of metal, so that proves number of equivalents. And as per law of equivalence, the number of equivalents of all the reactants and products should be equal. That's why I'm equating here. So that should be equal to weight of O2 divided by equivalent weight of O2. Okay. And that should also be equal to weight of metal oxide divided by equivalent weight of metal oxide. Done? Clear? And this is the equation I will use it, because this one and this one, if at all I equate it, that is more useful for us. So check. So what I could write, weight of metal, correct, divided by equivalent weight of metal. Equivalent weight of metal. Let me write down this as equivalent weight of metal. That should be equal to weight of metal oxide. Okay, so weight of metal oxide, that divided by equivalent weight of metal oxide. And you know that equivalent weight of metal oxide can be written as equivalent weight of metal plus equivalent weight of oxygen. And now you see, weight of metal divided by equivalent weight of metal. Okay, and he said that it is double that of oxygen. And you know that oxygen's equivalent weight is fixed, everybody, that is 8. So if it is 8, it is double the 8 of it, and that is equal to weight of metal oxide divided by equivalent weight of metal, which is double the oxygen, plus equivalent weight of oxygen is 8. So therefore, weight of metal by 2 into 8 is equal to weight of metal oxide divided by 3 into 8. Correct? So 8 will get cancelled. So 3 times of weight of metal is equal to weight of metal oxide. Okay? And that's what he said. The weight of metal present in it is how much? Okay, how many times its weight of its oxide is greater than. So weight of metal XY is equal to 3 times greater than weight of the metal. Correct? So 3 is your answer. Sorry, not 3, 3 by 2. 2 was also there. 3 by 2 is the answer. If you're finished, please check it out, write it on your own. Let me know if you have a doubt. 0.324 grams of copper was dissolved in nitric acid, and copper nitrate so obtained was heated and was converted into this much amount of copper oxide. Calculate the equivalent weight of copper. Okay. All that's a very simple question. There is a lot of learning in it. Okay. So let me tell you what is that. Check. So basically here there is some kind of a reaction happening like this. Copper solid plus HNO3 reaction is being done. It is forming some copper nitrate. Okay. With lot of other compounds might be also there, but it has been said that this copper nitrate, which is heated, correct? So it is becoming something like this. Okay, CuXOOY plus maybe NO2 plus O2. We don't know what are all the products we are getting. This is something which I'm guessing. One thing is for sure, as per the question, the information that is given is this one, and this one. Correct? Is that clear? So, see, if not too many details are given in the question, you will always assume that whatever the reactant is, this entire thing is first converted into this one. And this entire thing is next converted into this one. So, there is no residue here. Okay. Everything is converting going forward into that compound. So now, what is that you will relate here? Depending upon the data, what is the data given? See, 0.304 grams of copper. That means the data of the copper is given. Similarly, the data of the metal oxide is given. That is, copper oxide is given. Okay. But between nitrate or anything else, these are all any, in case if you have more such kind of reactions, that is all not given. But is it necessary? No. Why? When it comes to the same reaction, same reactant is going forward and forward to multiple reaction steps, you can still equate the number of equivalents. It does not make any difference. Okay, that means the number of equivalents of copper solid will be same as equivalents of HNO3 that was used, will be same as equivalents of copper nitrate that was used, I mean that is formed, and that will be equal to the equivalents of you know some copper oxide solid which was known, like this. So you should be able to equate the equivalents of all of them. Got it? Considering they are not remaining as residues. Okay. So if this is known, sorry, as per the question, the main relation what you need to check out is for these two. So how they are related to each other. So that's therefore I can say weight of metal in solid state divided by equivalent weight in of copper, right? That should be equal to weight of cop, you know, Cu copper oxide divided by equivalent weight of copper oxide. So that implies what is the weight of copper now? 0.324. That divided by equivalent weight of copper, right? Equivalent weight of copper, that's what is unknown to us. So let me simply write this as E of Cu. That is equal to weight of cuprous oxide, so which is 0.406. That divided by equivalent weight of copper plus equivalent weight of oxygen. Okay. And you know that for oxygen it is fixed. So 0.324 divided by equivalent weight of copper is equal to 0.406 divided by equivalent weight of copper plus 8. And you just need to solve it for equivalent weight of copper. Okay. So X is coming out. That means equivalent weight of copper is coming out to be 31.6. Okay. So valency factor of copper would be equal to, molar mass of molecular weight of copper, that divided by 31.6. So valency factor is equal to molar mass. Molar mass of copper is 63.5 divided by 31.6. So approximately you're getting this as 2. So the valency factor in this case is 2. Equivalent weight is 31.6. Please do check, everybody. So what we have is something like this. Metal M plus H2SO4 is forming some kind of a metal
Sir,
sulfate. Yeah.
I sent my answer. Can you check it?
Yes, that's right. Sorry, that's correct. Check. So weight of a metal is alpha grams. Here it is beta grams. So simply use the equivalents here. So weight of metal divided by equivalent weight of metal. That has to be equal to weight of metal sulfate divided by equivalent weight of metal plus equivalent weight of sulfate. Sulfate will be SO4 2 minus always. Hence, we can write this as weight of metal as alpha. Alpha by equivalent weight of metal is equal to, this is beta by equivalent weight of metal plus equivalent weight of sulfate. Remember that equivalent weight of the charge ions I told you. You just check it out. How much is the total charge it carries? So therefore, molar mass of SO2 is how much? 96 by 2. So how much it is? 48. So therefore, this plus 48. So from here, if you calculate equivalent weight of metal, it is coming out to be 48 alpha divided by beta minus alpha. Okay, so this will be the final value you should look out for. Clear? Right. Check. As we go ahead, we need to introduce few more important concentration terms. Although we have learned some of them in mole concept, let me quickly revise their definitions. Concentration implies what is the amount of solute present in the solution. It is also referred as strength of the solution. Now, it can be expressed in various forms that includes molarity, molality, mole fraction, gram per liter is one representation, percentage weight by weight, percentage weight by volume, percentage volume by volume, ppm parts per million, ppb parts per billion. Molarity is equal to how many number of moles of solute we have divided by volume of the solution. Okay, so therefore number of moles of solute is n divided by volume of the solution is v. While when it comes to molality, it is about how many moles of solutes we have divided by what is the weight of the solvent, not the solution, but the solvent itself. So number of moles by weight of the solvent. Okay. And molarity, we learned it as they are related by this formula. That is molality, small m. I mean, while representing the units, we usually write it with small m. So m is equal to 1000 times of metal divided by 1000 times of D minus m into molar mass of the solute. Okay, D is the density of solution, ms is the molar mass of the solute. Another thing we know that mole fraction, it is about number of moles of solute by total moles of solution. So this is the mole fraction which we learned. Now is the new term we need to understand known as normality. Normality is exactly like molarity, okay, except for one change here. Check. When we talk about molarity, we talk about number of moles per unit volume, correct? But here it is about number of equivalents per unit volume or for 1 liter of solution. So normality n will be equal to how many number of equivalent solute we have divided by weight of the solution. Okay. And number of equivalents of solute can be number of moles of uh, sorry number of moles of equivalents can be written as number of moles into valency factor, isn't it? And that's what we are trying to figure out using this basic definition of normality. Okay, unit wise, if you notice, units wise, normality will be always equal to equivalence, correct? Number of equivalents per liter, correct? So this would be the case. Just like mole per liter, now we have equivalents per liter. Next, check out the question. If 5 grams of NaCl is mixed with H2O to make 600 ml of solution, find the normality. Okay, got it? So how do I figure out that? I'll write it this way. That is equivalent weight of, you know, NaCl. Sorry, number of equivalents of NaCl. That is equal to 5 divided by equivalent weight of NaCl. Equivalent weight of NaCl is 58.5. This is the equivalent weight of NaCl because the valency factor is 1. Okay. And if you know the equivalent weight here, so equivalent weight of sorry, 1 second. Equivalence of NaCl is given 5 by 58.8 here. Now using this equivalent concept, we can figure out, what is the normality. So normality is equal to number of equivalents divided by volume of solution in liters, just like molarity. So that is equal to 5 by 58.5, that multiplied by volume of solution. Volume of solution is 600 ml. So 600 into 1000 to convert that into liters. Okay. So putting these terms together, so normality is coming out to be 25 by 3 into 58.5, and that will push close to 0.85 normality. N represents normality here. Okay. So it is very similar to the molarity what we discussed. So only difference is there it was number of moles, here it is number of equivalents. Next, what is the n factor of redox compounds? For n factor calculations, we only require the half reaction. Okay, that is n factor is the total net electron loss or gain per mole of a compound. Okay, so please remember the absolute definition for n factor. N factor is total net electron gained or lost per mole of a compound. That defines its n factor. Got it? Check this out. When you have H2C2O4 converting into CO2, this is how it has been given. In that case, check out for what is the charge for two carbons here. Because I need to check out for 1 mole of molecule, 1 mole of reactant here. I can't do it for 1 mole now. So I have to directly write it for 2 moles of carbon. So that is 2x plus 2 plus 4 into minus 2 overall equal to 0. So 2x is equal to 4, x is equal to, sorry, this is 6. 2x is equal to 6 and x is equal to 3. So 3 is the uh, oxidation state, as well as if you notice the change, how much it brings it. Check out. This carbon has x plus 4 into 2 into minus 2. 2 into minus 2 equal to 0. So x is equal to 4. So now you can clearly make out. So oxidation state is changing from 0 to, 3 to plus 4. So number of electrons transferred in this case is 1. So there is only one electron transferred, two electrons transferred from here to here. Now, why we need to take it as 2 here? Check out. Here I am writing it for 1 carbon here. But for 2 carbons, how much it will be? Actually, for 2 carbon, the charge will be 8. Okay, clear. So that should be 2 here. Got it? So that means for 2x amount of charge. For 2 carbons, the total charge is 8. Now here for 2 carbons, it is 6. So basically from 6, it is changing to 8. These are the number of electrons transferred. Understood? Not here. Here. You can see these are the number of electrons transferred. So here x is equal to 8. 2x. 2x equal to 8. Here 2x equal to 6. Number of electrons transferred are 2. Done? Everybody? Now, check this out. If you have cases of redox reaction, you should be able to figure out uh, per molecule how many electrons are being given or how many electrons have been taken. That means how much oxidation it has been done or how much reduction it has done. Correct? So you'll always measure in terms of how much oxidation and how much reduction that has been done. Clear? Check it out. If only one atom is undergoing oxidation change or a reduction change in this case. For example, if at all I'm talking about manganese in this case. The oxidation state of manganese is +7 and here it is +2. So if it has to go from 7 to 2, the number of electrons it should transfer is 5. Similarly, check out KMnO4 here, +7. Manganese here is +4. So number of electrons transferred are 3. And KMnO4, this is being +7, checking into +6. So the difference is 1. So valency factor is 1. I2 to 2I minus. Now this is very important. Check everybody. When I write I2, that means you need to check out for 2 moles how much is the charge. Why? Because 1 mole of I2 contains 2 moles of iodine atoms. So if it is about iodine atoms, the valency factor here is 0. And for 2 iodines, it is -2. So number of electrons transferred are 2. Got it? So the valency factor, how much is the electron difference here? Between 0 to -2, 2 electron difference. So that will be the valency factor here. Next, I minus is changing to I2. Now this time you will not take for 2 moles because I am supposed to always take it for mole of species. The species is I minus. So therefore, valency factor in this case will be equal to, this is 0, -2 to 0. So 2 electrons. So 2 electrons, 2 electrons are being transferred here. Got it? So that 2 electrons means -2 to 0 here, isn't it? So that will become 0 minus of -2. So that makes it 2. So that will be the valency factor. Okay. Next one also you check out for 2 iodines only. For 2 iodines, charge is 0. Right hand side there was actually one IO3 given, but it should always have same number of atoms on left and right hand side. So that's why I multiplied this with 2. So 0 changing to oxidation state of iodine. How much it is? 1 iodine is +2. So the total charge will be +10. So 0 to +10 means 10 electrons we have transferred. Correct? Similarly, when it comes to 2 sulfurs here. So 2 sulfurs is +2. +2 times of x is equal -6 equal to 0. So 2x is equal to 4. So x is equal to 2. So the charge on sulfur, for 2 sulfurs the charge is +4 because I need to check out for 2 sulfurs. While here for 4 sulfurs the charge is +10. So for 2 sulfurs the charge is +5. So number of electrons transferred is 1. So in this case electron has been transferred. Clear everybody? So I suggest please go through it once and try to figure out the rest of the valency factors everybody. Okay. I'll give you 5 minutes of time. Complete that. See the next one. Na2S2O3. I'm directly writing the values. You check, whether you got the same thing or not. Okay. So here it should be +4 and here it should be +12 because you need to check out for 2 sulfurs, not 1. Got it? So in that case, the number of electrons transferred would be 8. So that would be the valency factor. Here it is +7 changing to +2. So number of electrons transferred is 5. So 5 is the valency factor. Okay. Two chromates makes it +12 changing to +6 for 2 chromiums. So valency factor is 6. Dichromate 1 chromium, chromate 1 chromium is +6 changing to +3. So 3 electrons transferred. So valency factor is 3. H2O2, 2 oxygens. Now you need to check out for 2 oxygens. This is a peroxide, correct? So 2 oxygens will have total charge of -2, changing to 0. So that makes 2 electrons are being transferred. So valency factor is 2. Next, sulfate from +4, it is changing to +6. So 2 electrons are being transferred. So valency factor is 2. Copper here is +2, sulfur here is -2. copper here is +2, sulfur here is +6. So it is a sulfur which has transferred from -2 to +6. So total 8 electrons. So the valency factor is 8. Got it? Next, iron. If you notice, one iron is +2 oxidation state, and there are two irons here. So we can first calculate for 2 and then divide it by 2. Okay. So total it is 6 by 2. So which is 3. So +2 to +3, number of electrons transferred is 1. So valency factor is 1. Correct? Next, if we compare it with this one, so we have iron. 1 mole will have 0.93 moles of iron. So 0.93 times of X is equal to 2. So X will be the valency factor, which is 0. X will be the oxidation state. Got it? I hope this part is clear, everybody. Check out on the right hand side how much it is. So we have, for 2 irons it is +6, isn't it? For 2 irons it is going to be +6. But I need to find out for how much iron here, because 1 mole contains 0.93. So I have to again calculate it for 0.93. So that is 0.93 times of 3. So this will be the total charge of iron, because 1 iron is +3, but I require it for 0.93. So therefore, valency factor will be equal to 0.93 into 3 minus, how much is the valency factor here? For 0.93x, it is 2. So this will be the valency factor. See, let me remind you again. For 0.93x times, this is the total amount of charge on iron. That is given as 2. Okay. So valency factor will be equal to the oxidation state of the product minus the reactant here. Okay. So that will be the valency factor here. Next. Chlorine, here it is at +7, changing it to -1. So number of electrons transferred is 8. So the valency factor for perchlorate is 8. H2C2O4, here it is at +6, and for 2 carbons it is +8. You should always check out for 2 carbons in such case. So the valency factor is 2. Iron, which is at +3, because all 3 NO3 groups we have, and each nitrogen will have +5 oxidation state. So +5 into 3 is what I need to check, because there are 3 nitrates in it. And iron is at +3, so there is no change in here, but NO is at +2, so 3 into +2. Okay, so it is +6. So how much is that nitrogen's total charge? Here it is +15, here it is 6. So from +15, it is changing to 6. So how much is the valency factor? 9. Correct. So the valency factor is equal to 9. H2S. Sulfur is at -2 oxidation state, and one sulfur is +6, so 2 sulfurs will be +12. So total charge of electrons is 14 electrons. So the valency factor in this case will be equal to how much? Sorry, I need to check out for one sulfur only, my mistake. +6, so 8 electrons. Because there are not 2 sulfurs here, only one sulfur is there. Next, 2 nitrogens you need to check. For 2 nitrogens, the charge is -4, and here the charge is 0. So number of electrons transferred are 4. So valency factor is equal to 4. Next, chlorine. Chlorine changing from 2 chlorines, changing from 2 chlorides here. So one is +7. +7 into 2 is 14. So 0 to 14. So number of electrons transferred is 14. So valency factor in this case is 14. Nitrogen is -3, changing into +5, +8. So 8 electrons transferred. So valency factor is equal to 8. Clear? Next. This in the last class also I explained you aniline structure here, NH2. So this is how the structure would be. So in this case here it is gaining from this end, gaining from here and gaining from here. So that makes nitrogen as -3. Now while here, if you notice, it is getting oxidized. So N, clear, plus and minus. This is the structure. So for this nitrogen, the oxidation state is +5. So -3 to +5. Okay, sorry, not +5, +3. Because you can see it is gaining from here, losing 2 electrons here and losing 1 electron here. So -3 to +3, how many electrons transferred? 6 electrons transferred. So therefore, the valency factor for this is 6. Very important. Okay, usually we make mistakes here. So check out. Valency factor for the molecule is 6. Please let me know if anybody has any doubt in that. All the values are clear, everybody? Now, if you are comfortable identifying the number of valence electrons, how much is the valency factor, correct? So you will be very comfortable in solving redox electron balancing as well as complete balancing of the equation. Along with that, we will see what are the uh, other equivalent weight based concept questions. Okay, clear everybody? So right, today I'll stop it here.